Okay, we're going to pick up where we left off the other day, bonding of atoms. That happens, bonding of atoms happens strictly because atoms want to become like a noble gas. We sort of talked about that the other day. And atoms are going to do whatever they need to get there. They can gain electrons, lose electrons, or sometimes share. And electrons live in these outer spaces around the nucleus. We talked about that the other day also. These are called electron energy levels or electron shells. And the first energy level can hold 2 electrons at most. The second one can hold up to 8. And the third one can also hold 8. And so on. And if it holds 8, it's where it wants to be, unless it's in the first one, and it can only hold 2. And that's full. And it's very, very stable there. And then the second and third, if they get 8 in their shell or their energy level, it's said to be full and very, very stable. And that attains what we call noble gas status. It's so stable, and that's what every atom wants to do. And all of the bonding that occurs happens so that they can get there. That's their goal. All right. Here's some representations of atoms. Hydrogen, and these are all according to the periodic table. You can look on the periodic table because the periodic table is arranged according to this. Oops, I didn't mean to hit that. Hydrogen has 1 proton and also 1 electron. And so that 1 electron, by necessity, lives in this first energy level right here. And then helium, you see it has 2 electrons. And if you'll notice on the periodic table where helium is located, it's located far away from where hydrogen is on the periodic table, even though it has just 1 more electron. And that's because helium's first energy level is full. That makes it extra stable. It's like a noble gas. Notice lithium, it has 3 electrons, but look where that third electron is. It started a new shell because that first energy level, first shell, can only hold 2. So its third electron went into a new shell. And if you'll notice where it is on the periodic table, it falls just underneath hydrogen on the periodic table. Because you'll notice it and hydrogen share something in common. They both each have 1 electron in their outer energy level. We're going to find that that makes them extremely stable. All right. So if you have a metal and a nonmetal, a cation that needs to lose electrons to become like a noble gas, and a nonmetal that needs to gain some electrons so that it can become like a noble gas, then you can have what's called an ionic bond. And this happens because one of them needs to gain and one needs to lose. So one is going to have a positive charge when it loses its electron, and one's going to have a negative charge when it gains an electron. And this makes it have opposite charges, opposites attract, and this causes an ionic bond. These bonds are extremely strong and very important in our body. This particular one right here, sodium chloride, also known as table salt. All right. An ion happens because an atom needs to lose an electron so that it can become like a noble gas. Remember what their goal is. They want their outer shell to be full. And if it needs to lose an electron, like lithium that we had a couple of slides ago, it had 1 electron stuck out there by itself. And if it could just lose that 1 electron, then it would have a very stable shell. It would just have the 2 left, like helium has. And that's very stable because that's a noble gas. And so if lithium could do something to lose that electron, it would become like helium, very stable. So if lithium can lose that electron, it will be very happy. So if it can find a place to get rid of that electron at, it's going to do it. And then it's going to become a cation, positively charged, because now it's going to have more. I don't know what I'm doing here. I'm apparently not pushing the right buttons on this thing. Give me that. It's going to have more protons, which are positive, than it is electrons, because it gave one electron away. Okay? Notice that this happens when an atom loses electrons. Conversely, you have an anion. And anions happen because on the other side of the chart, if you have an atom that has, like chlorine here, it has 7 electrons in its outer shell. If it could just get one more, it could be like neon, or like in this case argon. And it would be so very, very happy, because it could have 8, and 8 means full. 8 means noble gas, and it would be very happy indeed. So it'll do what it has to gain an electron. And if it does, though, it gives something up. What it gives up is its status as an atom, because atoms must be neutral. So instead of being the chlorine atom, now it's going to have a charge, so now it's going to be called an ion. It doesn't mind it, though, because now it's going to be like a noble gas. So now it's going to charge. It's got a negative charge, a -1 charge, because it gained one negative electron. But it's okay, because now it's like argon. That's its goal. Okay? All right. And then when these opposites come together, they can form an ionic bond, which are very, very strong, by the way. All right. The other kind of bonding that happens is covalent. And here, look at these 2 hydrogen atoms. These 2 hydrogen atoms, if they can't find anybody to take their electron, they might be willing to share their electrons. Sharing electrons only happens in nonmetals, because nonmetals, they want to gain to become like a noble gas. But if they can't find anybody that's willing to give it an electron, then maybe they'll be willing to share. And notice where those electrons get shared. They get shared in between here. So now both of these 2 electrons, this electron is from this hydrogen atom, and this electron is from this hydrogen atom. So they're both feeling the hydrogen atoms. Both of them are feeling 2 hydrogen atoms, which makes them feel like they're helium. Even though they're both still hydrogens, they're both feeling like they're heliums. They're both sharing those 2 electrons, and they kind of get shared in the middle there. This forms what's called a covalent bond. Covalent bonds are very different from ionic bonds. They have very different properties, but both are important to our bodies. Water molecules, which is the most important substance in our body, are formed from these kind of bonds, where oxygen, a nonmetal, and hydrogen, a nonmetal, form these kind of bonds. Okay? Now, just like you can share things with different people at different times, covalent bonds can share. Sometimes they can share with just 1 atom, sometimes with 2. So covalent bonds are unique. All right. I'm going to give you some homework that has to do with this. I'm going to show you guys, or you're going to be learning how to do these structural formulas. Each of these lines right here represents sharing a pair of I hate us doing that. Each of these lines right here represents 2 electrons being shared. So there's 1 from this hydrogen atom and 1 from this hydrogen atom, 1 electron, that is, being shared in between. Instead of drawing those electrons each time, they represent it with a line between them. That line represents 2 electrons being shared. One line represents 2 electrons being shared. So notice this double line right here. Please understand what that means. That means 4 electrons are being shared between these 2 oxygen molecules. Now, if you got 4 electrons being shared between 2 oxygen molecules, that's going to be a stronger bond than just a single pair of electrons being shared. All right, here's water, very important in our body. You have a pair being shared here and another pair being shared here. This is carbon dioxide, also very important in our body. Our body makes carbon dioxide, it's what we breathe out. You got a double bond, 2 pairs being shared. These are called structural formulas instead of having to draw lots of dots. All right? Okay. And then if they're shared unevenly, like one's more of a bully and says, hey, I want those electrons closer to me, even though we're sharing them, let's keep them closer to me, that makes what's called a polar molecule. Because even though they're sharing them, like oxygen, for example, is a pretty big bully. And it's saying, yeah, even though we're sharing, I'm going to keep them closer to me. That makes that what's called a polar molecule. So even though this molecule is actually sharing, because these are the 2 hydrogens here and here, and this is the oxygen here. Oxygen's even bigger than hydrogen, but even though these are being shared, oxygen is saying, yeah, I'll share with you, but those electrons are going to stay closer to me. So it's pulling the electrons closer to it. So really, these 2 hydrogens are feeling like they're positive. And there's this funny looking thing called a sigma that says it feels positive. It feels positive. And there's this sigma here that says it feels negative on this end. Those are called sigma. And this makes it polar, which means this, when this is going around, it's kind of like a magnet. And so if you got another oxygen molecule, another water molecule here, that it wouldn't stay turned this way, because these 2 positives, here's the positive end right here, and here's a positive end right here, and here's the negative feeling end over here. These 2 positives right here would not want to be close together. So this water molecule right here would turn so that the negative end would be close to this positive end. So it would turn more so that the oxygen would be over on here, like so. So water is going to orient itself so that this positive end will be closer to this negative end down here. Okay? And so polar molecules are very important in our body. Lots of important stuff happens because of those bonds. And then hydrogen, this is a perfect showing of how these positive parts of the hydrogen, see how this is the positive feeling? There's our positive feeling of hydrogen, negative feeling oxygen, positive hydrogen, negative oxygen. See how these little dotted lines here are not true bonds because they can't bond together. They're already bonded to the oxygen and the hydrogen, but they can feel attractions because that feels negative and it feels positive. These right here, this weak attraction between the positive and the negative ends of this pole are formed between water molecules, and it makes water so incredibly special. And it makes water have very unique properties. Okay? And these important, very important in the structure of DNA and of other important nucleic acid structures. So important. in our proteins, gives water an extremely high melting point, an extremely high boiling point, much higher than it should be. So unique out there in the world. All right. I'm pretty sure that's as far as I want to go today. Yeah, it is. So I'm going to give you some assignments. I hope you have a great day.